Today I'm going to be talking about building how we build and deploy ML applications, and specifically how we've done this with case law. So my name is Taylor Arnett. I direct the software development at AltaML. And what AltaML is it's really this, it's a company that has a lot of different initiatives. I touched on earlier, we have this applied AI lab. We also have sort of a solutions part of the business, but in all, the whole purpose of AltaML is to apply artificial intelligence to elevate human potential. And elevate is a really key word here. So we focus on industries and opportunities where we think that applying ML can actually benefit humanity. Now, again, like I said, AltaML's business is a little bit unique, and especially how we generate opportunities. The most well-known part of AltaML is our services department. We come across hundreds of ML use cases across various industries with really big partners. And we do that through our client engagements. Another part of AltaML, which is going to be kind of the focus of this talk, is an area we call product. And that's where we commercialize these opportunities and focus on products. So I'm a part of the product team, and my role and responsibility is really on the technical execution of growing these ML ventures. So again, just a little bit more on the product here. We have all of our venture opportunities go through this pipeline. And across this pipeline, we have various teams that are engaged across this at each stage. So earlier on, we might have venture analysts, product managers, and designers really just assessing the commercial viability, and even just what kind of like the prototypes of what these products could be. We try and get client feedback. We do some customer discovery, really make sure that this is something worth working on. And then from there, as that graduates closer to the alpha stage, that's when we really start bringing in more technical staff. So we also assign a venture lead who kind of acts as the mini CEO of this venture. And this is where the data scientists and software developers will really start to build the product and hopefully release an MVP. So for the rest of the talk, I wanted to, I know this talk is supposed to be technical, so I wanted to actually pick an example of something that we're currently building right now. And this venture that we're working on is in the legal space, particularly within case law. Just so everyone here has context, case law in Canada, it's an ever evolving field. There's new judicial decisions that constantly evolve and change how the law impacts, or how law impacts modern life. So case law research is integral to understanding and practicing law, and finding the right case to, win your point as a litigator, but also try and find justice in the court system changes how the court operates in the future. So, something might go to the Supreme Court and get overturned, and that becomes a binding precedent for all other layers in the law across Canada. So understanding and researching law is extremely important. So, well, we think, and researching law right now with the standard tools, it's a lot like finding a needle in the haystack. There's a lot of cases to go through, and the tools to do that aren't great. So we think that machine learning, and specifically natural language processing, as well as modern software design and tooling, can really enable litigators and legal researchers to perform case law research a lot faster and a lot more thoroughly. And for this product, we're focusing on delivering this value through three main buckets here. So we have semantic, searching, case law analytics, and workflow tooling. So to jump into each of these a little bit, right now, researchers, how they perform case law research is really just through keyword search. And as they want to get more specific, they have to do really, really exact Boolean operations. And all of this is in an attempt to surface really relevant cases that might be relevant, that pertain to their research or their target case that they're working on. But we think that using NLP, we can generate a language model where these researchers can actually search using the phrases, general ideas that they want to search for, kind of like a question and answer type approach. And in order for us to really test this hypothesis, start building it, we need a lot of data. So to embark on this path, we got access to hundreds of thousands of case law documents. They range back many decades here. And this quantity of data actually allows us to generate a pretty accurate model. We used a doc-to-vec NLP technique to chunk every single case into its paragraphs, and then from the paragraphs, all of the sentences. Now, once we have all of these sentences split out, We vectorize each sentence along with its sentence identifier and pass it through a shallow neural network to train the weights for the end model that we'll be using for the predictions. So this is an unsupervised NLP technique. And just to give a sense of the scale here, the vector that it outputs is 300 dimensions, and we have dozens of millions of sentences within our model. So the visual on the right here it's just a visualization of what a vector space looks like. Again, ours is 300 dimensions, so this isn't quite accurate, but it gives a picture of sort of the size and the quantity of data points that we have. Now, once we have this whole vector space, what we do here is we pass through the semantic search, we vectorize that search, we basically put that into the vector space, and by using a nearest neighbor algorithm, just cosine similarity, we basically return the top 1,000 most relevant other sentences and then get the distinct cases from there. So that was all very data science heavy, but we do have more traditional software engineers really take these models and start to productionize them. So in this particular case, we wanted to actually serve this semantic model through an API. So since we're in the MVP stage and in ML deployment, you can get some very sophisticated workflows. For us right now, because we're sort of in this very early stage, we just want to get something that works, but also is out there so we can get feedback from clients before we really start investing in really complicated pipelines. So just keep that in mind as we go through. This is going to be kind of slimmed down and simplified quite a bit. But we decided to wrap this semantic model in a fast API, which is a super fast Python web framework that leverages asynchronous Python. And we just wrap the model with this API. And once we have that, we can take a simple, post request with the query. In this example, it's a legal recourse for internet harassment. We take some pagination parameters. You can also pass some filters if you want to, restrict this to certain courts or certain dates. Now our model returns, in this case, 1,000 results with some pagination information and the matches, which are basically the case IDs as well as the confidence score along with them. So great, we have a way to do semantic searching, but there's more that we want to do, and that's just an API at this point. So searching is awesome, but once we have a given case, we want to be able to help legal researchers find a lot more information within that case. And there's a lot of really helpful information within particular cases. So for example, we know that within the case, there's other citations. So what other cases cite this, or what other cases does this case cite? There's subject matters, there's the names of judges, there's the names of the courts, there's subject matter and things like that. But also a little bit more abstractly than that, all cases follow a predefined pattern. They typically have 5 main elements, which are we call FILAC, and they're the facts, issues, law, the analysis, and then the conclusions. So that is really what researchers are looking for when they have their given case, and they're looking for other cases that are similar to it, are relevant to it in terms of the facts, it's in terms of the outcome that they're looking for. So they really want to find relevant documentation this way, or documents this way. So unfortunately, all of this data is purely unstructured text data, so we can't extract much information without using even more ML. And we built another model. This is actually a supervised model, but what it does, it extracts all these valuable entities. And we basically took a pre-trained model, did a lot of transfer learning here, fine-tuned our algorithm, and got identified pieces of the text that we care about. And I wanted to share that because it's these types of, these finding like existing tooling like that for early stage projects is so important, because generating a language model with this much data costs a lot of money, and it takes a really long time to train. So we're always trying to find ways to speed up the process. Now, the idea is, and what we've done actually is once we have all these entities extracted, we can really start graphing them in terms of, okay, the cases, the courts, the judges, those are all nodes within the graph. And then the relationships between them, like the case cites other case, this judge oversees these cases. Those are all the different edges of the graph. Basically, this just becomes a typical graphing problem at this point. And the nice thing about graphing problems is there's a lot of existing tools out there for interfacing with those. So we use Neo4j as our graph database. We uploaded all these different entities in there, and that lets us to query this graph structure to help surface a lot of really helpful insights about any of the cases. So an example of this flow really is, we have a GET request. Maybe you have a particular case. You want to get some citation stats for that. Now we have a different fast API web server here where it's just hitting Neo4j with different Cypher queries. And these Cypher queries return all the different cases or whatever you've specified in your query statement. And then our fast API server would then respond to that GET request with maybe the number of citations for this case, which cases in different levels of court cited this. And in that particular example, that's quite helpful because depending on which other cases cite this case and the levels of courts of that those cases come from, it really helps litigators and legal researchers understand if this case could be precedent or not. Like, how relevant is this, and how will the judges look at this in terms of my defense or my arguments? Last piece here. So we have two APIs here, and we want to tie this all together. And this is a bit more of the software approach here. We want to add a lot of value by integrating these different tools in a nice workflow tool. So again, a little bit of background. We've discovered that lawyers do a lot of their research on websites like Canly. That's where they can read through the existing cases. So we've built a Chrome extension. It's just an Angular application here. It's very similar to something like Evernote, where you can start your research sessions. It kind of tracks your activity here. We're using Firebase right now to store all of this data. You can add cases to your research. You can add notes and highlights and things like that. And that's to help you sort of do better research when you're online. But the really big value add is when we tie that into Word add-ins. So researchers, like majority of law firms all use Word when they're working on their cases. So we thought it'd be really awesome if we build this Word add-in. Our first version is built, but we've just got a designer to redo the wireframes and everything. So I do have some images of the wireframes, but essentially what we're doing here is we're bringing in all those cases that are in their sessions. You can see in the third slide here, we're using some of those citation metrics within a particular case. You can see how it's been cited over time. In this example, it's actually been trending down. Maybe this case isn't worth bringing in court. Maybe it's not really as relevant anymore. There's a head note section in there. We'll have the different FILAC pieces really on hand in the document that the legal researchers are working in. And then as well as another searching functionality. So that's where they can do the semantic searching with the filters without ever having to leave Word. There's a lot of technical details that I could go into in all of this stuff, but I wanted to keep this kind of at a high level. This diagram kind of shows the different pieces that we have in place here. So we have two Angular applications, and then on our back end, we host everything in our Kubernetes cluster. We scale based on demand there using Kubernetes pods and all the benefits that you typically get with Kubernetes. And we have Neo4j for our graph database, and we also use Elastic because we do some things with our searching algorithm to also try and compare our results to keyword searches and try and surface the most relevant thing for the client. And then we release our software. We're a big GitOps firm, so every kind of commit to main goes to our staging servers. Every tag push to main goes to our live servers. We use Flux, which is a Kubernetes operator, to do all of that GitOps work for us. And we can deliver really, really quickly, and we just love it. So again, that was just one particular example of a project we're working on. AltaML is doing really cool things in the veterinary space. We have another product that's very shortly coming out. We work in the health industry and across a bunch of different industries here. So again, this legal product is just one of many. So if this interests you, working with data science, working with machine learning, please check out our website. We are hiring for the following positions, and thank you very much for your time.